Hello everyone, I'm Sang Kim at Guide Wave Analysis LLC. Today, I would like to present the clarifying material dependency in the guide wave generation for pipeline testing. This presentation includes three main things. First, addressing a common misconception about MSS guide wave testing. Second, live demonstration of ultrasonic wave generation on steel and glass plates using MSS guide wave testing system. Third, explanation of wave propagation in pipe wall. Let me address a common misconception. This is an example of a common misconception found in the industries. The effectiveness of MSS magnetostrictive sensor technology can be influenced by the material properties of the structure being tested. It works best with ferromagnetic materials, which may limit its applicability in some non-ferromagnetic structures. The statement suggests that MS technology effectiveness is restricted to ferromagnetic materials, which is incorrect. This is often propagated by those unfamiliar with the physics behind the guide waves or who primarily use piezoelectric technology. Let me clarify, MS technology is capable of generating guide waves in both ferromagnetic and non-ferromagnetic materials. Let me prove these clarifications with a live demonstration. This is our live demonstration of wave propagation on both steel and glass plates using the guide wave testing GWT system with a magnetostrictive sensor or MSS probe. Here we are working with an MSS probe specifically designed for high sensitivity inspection of pipelines or plates of pressure vessel and tank. This probe generates a magnetic field directly beneath it. And when there is no ferromagnetic material attached, we only observe the initial pulse in the live signal. However, when we attach a ferromagnetic strip, mechanical vibrations are created within the strip as shown in the live data. To produce ultrasonic waves with this setup, we couple the ferromagnetic strip to the plate or pipeline surface using shear couplant, mechanical coupling, or epoxy bonding. When we position the MSS probe over the bonded strip on a steel plate, guide waves are generated and propagate along the plate, reflecting back from its edges. Similarly, when we move the probe to the glass plate, the guide waves travel across the glass, reflecting back from both ends of the plate. This demonstration visually confirms that the MSS probe effectively generates and propagates guide waves in both ferromagnetic and non-ferromagnetic materials. Now let me explain the details of wave propagations. What are the mechanical waves? Mechanical waves are the propagation of local deformation through the medium. If the medium is air, it is a sound wave. The ultrasonic waves are propagation of local deformation in material and mediums. The guide waves are propagation of local deformation in structure such as a pipeline, plate, rod, cable, etc. This slide compares generation of waves. First, direct generation. Sound waves in air are directly generated by local deformations such as clapping hands or speakings. This type of wave does not require couplings, as the local deformation in the air itself generates the wave. Second, indirect generations. Guide waves, on the other hand, are generated indirectly using sensors such as magnetostrictive, MSS, or piezoelectric probes. These waves require couplings to transmit local deformation from the probe to the structure being tested, such as a pipeline or plate. The coupling ensures that the energy is efficiently transferred from sensor to structure to generate a guide wave. This is a schematic drawing of magnetostrictive and piezoelectric properties of material that are used for guide wave testings. First, magnetostrictive properties. The magnetostrictive materials, typically ferromagnetics, exhibit the property of generating magnetic field when they undergo mechanical deformations. Conversely, they are also deformed when exposed to external magnetic field. This property is utilized in the magnetostrictive sensor MSS for generating and detecting guide waves in structures. Second, piezoelectric properties. Piezoelectric materials such as quartz or ceramics generate electric voltage when deformed mechanically. Similarly, these materials deform when subject to electric field. This characteristic is key in the piezoelectric transducers for generating and detecting ultrasonic and guided waves. Both magnetostrictive and piezoelectric probes are not influenced by the material property of the structure being tested because the waves are generated indirectly. This slide shows a schematic drawing of generation of ultrasonic waves in the pipe wall using couplings. For transmitting guide waves on pipelines, we use 3 couplings of shear couplant, epoxy bonding, and dry coupled probes. By changing the probe alignment, spacing, and coverage of pipe circumference, both magnetostrictive and piezoelectric probes can generate longitudinal, torsional, and flexural mode depending on the field testing requirements. Let me summarize my presentations. First, the guide wave testing method utilizes magnetostrictive sensor MSS and piezoelectric transducer for generating and detecting ultrasonic waves in pipelines. Second, probe coupling. Guide wave probe can be coupled to pipeline using mechanically dry coupling, shear couplant, or epoxy bonding, ensuring effective wave transmission. Third, material independence. Contrary to common misconceptions, both magnetostrictive and piezoelectric probes are not influenced by the material property of the structure being tested because they are generated indirectly. Fourth, mode generation. Both types of probes can generate longitudinal, torsional, and flexural mode depending on the specific test requirement in the field. Fifth, correcting misconceptions. It is crucial to address and correct misinformation spread by inspectors or industry professionals who lack fundamental understandings of wave physics. Thank you for your attention. If you have any questions, please email me at skim@gwanalysis.com. Thank you. Bye.